Okay, good evening, everybody. I thought that I would go through this presentation now to kind of help you out, maybe to shed a little bit more light on than just running through it yourself. We talked about this in the WebEx meeting. I'll do a second presentation or demonstration of just working out some of the problems by hand, just in case you want to see some extra stuff. I'll put that up tomorrow. All right, but let's go ahead and get started with the presentation here. So we're going to start off talking a little bit about preferred sizes. Preferred sizes basically were instituted or standardized as a response of the manufacturing that was necessary for World War II. And basically what happened, it makes sense. The manufacturers decided that in order to streamline and make more efficient their manufacturing process, they wanted to standardize certain parts. And here we're talking about cylindrical mating parts. Okay, that's really the important parts that are going to be used in machinery. And so they basically said that we're going to standardize these sizes so that there's a set number of sizes that you can use, and you just have to decide which one you want to use within that standardized set. Obviously, the start was with fractional. Back in the World War II era, dimensions were fractional. There wasn't really any kind of digital at all. There weren't computers. And then later, decimal inch came in, and we have computers and now CNC. And so this is really the same thing. Decimal inch and fractional inch preferred sizes. Obviously now we're using decimal inch. But these are what engineers and designers use when they're looking to start designing things and want to use a standard size. The benefit here is that we have tooling that is made for these standard sizes. So everything becomes cheaper, everything becomes easier, more standardized. Okay, this led to the need for a determination of standard fits. All right, so once you have a standard hole size and a standard shaft size, the hole goes into the shaft, or the shaft goes into the hole, and we need to standardize the fit between those two parts. So when we talk about fit in this case, we're talking about the fit between a shaft and a hole. Okay, and we characterize that fit by whether it is tight or loose. Okay, a tight fit may be a tight fit that can still rotate, or it may be a press fit where you're going to be inserting the shaft into the hole, and it's intended to be a permanent fit, a press fit, or an interference fit. Okay, this also improves efficiency of manufacturing. It reduces design and manufacturing costs, and all the good things come from that. Now, here's a little illustration of what we're talking about. So in this case, you can see the bushing is going to be press fit into the pulley. So that would be an interference fit. And then the shaft is going to have a clearance fit. So it's going to be able to rotate clearly or easily within the bushing. Okay. Now, moving on to some definitions. Let's first talk about the definition of maximum material size. Okay, this is a critical concept in dimensioning, especially geometric dimensioning and tolerancing, if you take the MGT 115 class later on. But the concept of maximum material size is that it represents the size of the feature that results in the most material present. Okay, so if we look at this example right here, we have a shaft and a hole. Remember that all parts now have to have a tolerance. That's a rule in the standard. Okay, so the shaft has a tolerance of a diameter of 2,000 or 2.004 to 2 inches. Okay, and the hole has a tolerance of 1.997 to 1.994. Okay, so the maximum material size for the shaft, resulting in the most material in the shaft, would be its largest size, right? This is when the shaft is going to have the most material present. The maximum material size for a hole is going to be when the hole is at its smallest size. Now, if you think about this, that means that the material around the hole is going to be maximized. You're going to have the most material surrounding the hole. And so that's why the hole MMC is its smallest size and the shaft MMC is its largest size. Okay? Now, going forward from that, we can talk about a couple of different things, okay? So we can talk about allowance. Allowance is the intentional difference between the maximum material sizes of mating parts, okay? So if we go back, let me just go back to the previous. So the allowance between this would be the difference between 2.004 and 1.994, right? 2000 or 2.004 minus 1.994 is going to be 0.010, okay? So that's the allowance of this. The clearance fit is the size of the negative feature. That is when the size of the negative feature is larger than the positive feature in the entire range of allowable sizes for the mating parts. So again, let's go back to this, okay? So is this a clearance fit? Well, that would mean that in all the size range here, the shaft, which is the positive feature, has to be larger than the hole, which is the negative feature. And clearly, at no time is the shaft going to be smaller than the hole. 2 inches is never going to be smaller than 1.997. Okay. Interference fit is when the size of the negative feature, that is the hole, is smaller than the positive feature in the entire range of allowable sizes. So in this case, this is an interference fit because the hole is never larger than the shaft. Right? So this is intended to be an interference fit. The hole is always smaller than the shaft. And finally, a transition fit is when the mating parts have some clearance and some interference depending on their exact sizes that they're produced at. Okay. Last is a line fit. A line fit is when the fit resulting in either the clearance or the surface contact between the mating parts. Okay. That's kind of a special situation. We'll talk about that when we come across it. All right, so let's move forward to some mating part terms. All right, so we're looking at a shaft and a hole here. And here, if we just look at this, we can see right away what is the largest size of the shaft. It's 1.248. And the smaller size of the hole is 1.250. These represent maximum material sizes. So the maximum material size is 1.248 for the shaft and 1.250 for the hole, right? Clearly, if this is the maximum size of the shaft and this is the minimum diameter of the hole, this will always be a clearance fit. And we can calculate the shaft tolerance. The shaft tolerance is 1.248 minus 1.247. Which is 0.001, 1 thou. Okay. The hole tolerance, we can subtract these two numbers, and we also get a value of 1 thou. All right, so the shaft tolerance is equal to the hole tolerance equals 1 thou. All right, so the tightest fit is going to be when we have the largest shaft going into the smallest hole. That will obviously result in the tightest fit of those two parts, right? So that would be 1.250 and 1.248. The loosest fit correspondingly would be the opposite. It'd be 1.251, the largest hole, and the smaller shaft, 1.247. Okay. So then the allowance from this, we already talked about it, is 1.248 minus 1.250. The MMC size of the shaft minus the MMC size of the hole, actually reversed, MMC size of the hole minus the MMC size of the shaft is 2 thou. That's the allowance. And that's the tightest fit. Right? The maximum clearance is going to be the loosest fit. Right? Maximum clearance allowance. The allowance is also known as the minimum clearance. All right. So in inch fits, we talk about 3 different types of fits, right? We can have an interference fit, we can have a transition fit, and we can have a clearance fit. All right. Not a line fit. A line fit is when these two numbers are the same in this example, but a clearance fit is the 3rd type of fit. All right. Now, these equations are important. They're mentioned in your book, but they're kind of buried. So this slide you might want to keep up. We'll refer to it again in my next video, but these are the fit equations. The minimum clearance between 2 mating features is going to be the minimum hole minus the maximum shaft. Okay. Between 2 mating cylindrical features, the minimum clearance is the smallest hole minus the largest shaft. The maximum interference is going to be really the same numbers, but we're reversing their order. Now, why would we reverse the order? Well, here, because we're talking about a clearance, the hole is always larger than the shaft. So we put the hole first so we get a positive clearance. In the interference, the shaft is always larger than the hole. So we put the shaft first before the hole in this equation so that we have a positive number for the interference. Okay, and the allowance is just, well, look, it's the equivalent to the minimum clearance equation, min hole minus max shaft. Note, though, that the allowance can be positive or negative. If we have a negative allowance, then that means that it's the maximum interference, because these are the same numbers. Okay. Another way to state this is the minimum clearance is equal to the MMC of the negative feature minus the MMC of the positive feature. So what's the negative feature? Well, that's the hole. And the positive feature is the shaft. Now, if we look back, hole minus shaft. MMC of the hole minus MMC of the shaft. Max interference, MMC of the positive feature of the shaft minus the MMC of the negative feature of the hole, and then allowance. So this is an easy way to remember it. The minimum clearance is just a difference in MMCs. Maximum interference, the same difference in MMCs. You just got to make sure that you don't have a negative number. So if you get a negative number, that just means you got these in the wrong order. The allowance, hey, that can be positive or negative. If you get a negative number, then it's max interference. All right, so in inch fits, standard inch fits, there are, we talked about the three different conditions, clearance, transition, and interference. Clearance, they have two types of clearance fits. They are a running or sliding fit, and a locational or locational clearance fit. The running or sliding fit is symbolized by RC, and it ranges from RC1 to RC9. Locational clearance fit is an LC, and it ranges from LC1 to LC11. Transition fit is known as the locational transition fit, and its symbol is LT, and it ranges from LT1 to LT6. And then we have two types of interference fits. We have a locational interference fit, LN, and a force or shrink fit, FN. These range from LN1 to 6 and the FN1 to 5. Okay, so how do we use this in our designs? All right, so let's look at this right here. So we can see how this is a graphic depiction of the range of sizes for the clearance fit, right? An RC fit. So you can see an RC fit is going to be a much closer clearance fit than an RC9 fit. All right. So the way to understand this is the hashed symbol is the hole, right? And the solid symbol is the shaft. The hole, by being above 0, is always going to be the largest one, right? And so here we have the difference right there. The gap right in there is the clearance, the amount of clearance between the shaft and the hole. And you can see the clearance grows. So an RC9 is going to be a very, very loose fit, and an RC1 is going to be a tight clearance fit. Locational clearance locational fits, again, they range from a line fit for LC1, LC2, and LC3, and LC4, and LC5. Those all have line fits, and going to larger clearances up to LC11. Transition fits. Now here's where, look at that. What is the black solid? That is the, let's go back. That is the shaft, and the hashed is the hole. So here we have the shaft is starting to get into the size for the hole. So this is why we have transition fits, right? And here we have interference fits. This is an LN fit, and you can see there's a little bit of a transition fit here. Still a little bit of a transition fit. Now this is a case where the shaft is always larger than the hole. So this is clearly just an interference fit. And then these are force or shrink fits. FN3 is a very big or tight shrink fit. This is somewhat less of a shrink fit. All right, so how do we use these? What are the fit calculations? Okay. So the fit calculations, let's take an example right here. Okay, so we have a shaft 1.495 to 1.4925, and a hole of 1.5040 to 1.5. Okay, we can see just by inspection here that this is going to be a clearance fit, right? The shaft is always smaller than the hole. At no time does 1.495 go above 1.5. All right. The basic size for this is 1.5. How do we know that? Well, that's going to be given by the calculations, by the designer, right? And in this case, it's going to be the minimum hole, 1.5. All right, so here we can do the calculations on the shaft tolerance, which is 0.0025, which is the difference between these two numbers, and the hole tolerance, 0.0040, which is the difference between these two numbers. All right, so very easy. We just subtract 1.5040 from 1.5, and we get 0.0040, 40,000. If we look at the largest shaft and the smallest hole, that's going to give us the tightest fit. And just looking at allowance, that's going to be an allowance of 0.0050, a positive value, so that means we have clearance. And the smallest shaft and the largest hole is going to be the loosest fit, the maximum clearance, and that's going to be 1.4925 minus 1.5040, or 0.0115. Right. Now, let's do another example, but this time we'll use the tables. And this is what I'll go over tomorrow in another video. But if we start with an example of a fit that is a 2.5 RC9 fit, okay? So the 2.5 tells us the basic size. That's a 2.5 inch basic size. And RC9 tells us the type of fit that's going to be. So we know already that that's going to be a clearance fit, and it's going to be very loose. RC9 is a very, very loose fit. So we go to our tolerance tables, and these are in Canvas, okay? And use the ones in Canvas, not the ones in the back of the book. Remember, we have problems with the ones in the back of the book. And so we can see this is the table from Canvas, and we're going to go down to the nominal size range, and we want to find 2.5, all right? And so RC9 is this column, and 2.5 is going to be within this range right here. So we kind of triangulate, and we get these values right here for the hole and shaft limits. Now, this is a little confusing, so I want to be clear that we understand this. These numbers are not in inches. These numbers are in thousandths of an inch. So we have to move the decimal place when we use these. We can't use these numbers as they are, 7 and 9 and 13.5. Nothing will work, all right? So you have to move the decimal place here. So we'll talk about that in the next example, but this is the end result, right? So the 2.5 is the hole size. How do we know that? That's the minimum hole, because that's plus 0. And then the maximum hole is 2.5 plus 0.0070. That's how we move the decimal place here, 0.0070. So there we have that. And then the shaft is going to be 2.5 minus 0.0090 and minus 0.00135, all right, or 0.0135, sorry. And then you get those numbers. All right. So let's move on to the next example. There we go. We'll do we'll stick with 2.5, but this time we'll do an LT3 fit. So we find LT3 right here, and we go down to 2.5, which is right in that range, and we triangulate, and we find that these are the numbers, right? So what we're going to do here is to find the hole limits of size, we're going to add and subtract these numbers to 2.5. Now, not specifically these numbers, but we're going to subtract 0. So that's 2.5 minus 0, which is 2.5. And 2.5 plus 0.0012. So that gives us that number right there. And then we're going to do the same for the shaft. 2.5 plus 0.0008. and plus 0.0001. 2.5 plus 0.0008 and 0.0001. And those gives us our shaft values. So that's all we're doing. We're really just taking our basic size, which is going to be given, in this case is 2.5, and we're adding and subtracting these numbers to the hole and the shaft. The critical thing is to remember to change these numbers to thousandths of an inch. Okay. All right, so let's see. We got a couple more slides to go. Let's do an LN2 fit. Again, 2.5. So we do LN2. We go down to 2.5, so it's within that range. We find these numbers. They're in thousandths of an inch. So we're going to take 2.5 and we're going to subtract 0. And we're going to add 0.0012. There we go, right there. And we're going to take 2.5 for the shaft, and we're going to add 0.0021 and 0.0014. And those are the numbers right there. All right. All right, so what we've been doing for those examples is what's called the basic hole system. And the basic hole system basically says that the basic size is equal to the minimum hole diameter. All right, so back in these examples right here, this is the basic size, 2.5. So that is the minimum hole. And you can see that because we're adding and subtracting 0. All right, so in this example, a 0.50 clearance fit means that the basic hole system, the basic size is 0.5 right there, and that's the minimum hole. There's also a basic shaft system. Now the basic shaft system requires a little bit more work, okay? And we use the basic shaft system when 2 or more fits are required on the same shaft, okay? Now let me just say that we're not using this system for our vacuum engine design, okay? But when you use the basic shaft system, the basic size is equal to the maximum shaft diameter. And we know that we're using a basic shaft system when we put an S on the end of the clearance characteristic. So instead of an RC7, we're going to put an RC7S for shaft basis. All right. The problem with this, or I shouldn't say the problem, the difficulty with it is you have to manipulate the tables. Okay, so let's look at our example, a 2.5 LN2S. So the basic size is 2.5. This is a LN fit is a locational interference fit. So that means it's a little bit of a loose interference fit, level 2, and it's a shaft basis fit. So we're going to use the same tables. These are the only tables we can use. And we're going to find LN2, and we're going to go to 2.5, and we're going to find this area right in there. But we can't use these numbers as they are. All right. So what we're going to do is we're going to subtract the 1.2 from the 0 and the 2.1 from the 1.4. All right. And we're also going to use these numbers right here from the limits of interference. Again, all of these are in thousandths of an inch. So when we subtract the whole, we're going to take 1.2 minus 0, 1.2 minus 0, and we get 1.2 again. All right. That's easy math, but it's not 1.2. Remember, it's 0.0012. We have to move the decimal place. That is the hole tolerance. The shaft tolerance is done the same way, 2.1 minus 1.4, 2.1 minus 1.4. Now, if you're wondering why I'm putting the plus and minus in there, because technically you need to keep track of that, right? Here, it kind of works out, but in the next examples, it won't. All right, so 2.1 minus 1.4 is 0.7. No, 0.0007. Move the decimal place, and that's the shaft tolerance. The maximum shaft is 2.5. Where do we get that from? Well, that's given right here. This is the maximum shaft, 2.5. So boom, that number comes right down here. The minimum shaft is equal to the maximum shaft minus the shaft tolerance, right? We know the shaft tolerance equation is max shaft minus min shaft, so we just change up that equation and solve for the minimum shaft. 2.5 minus 0.0007 right here. And we have the minimum shaft is 2.4993. Now we have to use these numbers over here for the limits of interference. So we'll use the 2.1 number, which is the maximum limit of interference, maximum interference. change the decimal place, 0.0021, and we find the maximum interference is equal to the maximum shaft minus the minimum hole. Now, if you're wondering where I got that equation, go back a few slides. Remember all those equations that I gave you. That's the maximum interference equation. We plug and chug. 0.0021 is equal to 2.5, right? Right here, 2.5 maximum shaft minus the minimum hole. We solve for minimum hole, 2.4979. Boom, we're done, right? We know the maximum shaft, we know the minimum shaft, we know the minimum hole, and now because we know the hole tolerance, we can calculate the maximum hole. And there's our solution. All right. Now, obviously, this requires more work than the hole basis fit because these tables are designed for hole basis calculations. If we do shaft basis fits, we have to manipulate the tables. All right. So that's it. Review that. Right. If you have any questions about it, please make sure you email me. Tomorrow, I will put a video together of just working out some of those problems. And we'll talk a little bit about what are the problems that you're going to be using these in for the vacuum engine. All right. Let me know if you have any questions. I'll talk to you tomorrow.